Okay, let's continue and let's see how we can make use of the binary search tree and build another sorting algorithm. Okay, and then actually this is really easy. And assume that you have an array of A and then the length of the array is n. Okay, and then when you are trying to do a sorting algorithm, and the first step will be for each of the value in the array of A, you want to insert that into a binary search tree. In other words, you are going to take all the values one by one and then use those values to build a binary search tree. And after you have a binary search tree built using those values as the keys. What's the next step? You want to do an in-order tree walk. And because when you are doing a in-order tree walk and you are visiting all the values from the smallest to the largest, right? But anyhow, you can visit all those values, and instead of printing those values, you can put all those values into a new array. And then for the new array, those are the values sorted. Okay, and then let me use this example again. And let's assume that, well, after we have already put all the values into a tree, and then we have such a structure, and then when we are doing the in-order tree walk, we are gonna have 1, 2, 4, 5, and then we go to the right side, we have 6, 8, and 10, right? So we only have to grab all the values and then use those values as the keys, build a binary search tree, and then we do a in-order tree walk and keep all those values into a list, and then that list is the sorted list of all the values. So this sorting algorithm is really easy, isn't it? Okay, and then let's come back to our lecture notes. And my question is, how do you argue that for this binary search tree based sorting algorithm, this is also omega n log n? So I can tell you, it is omega n log n. And why? Okay, and for the omega n log n, what does that remind you? It reminds you this is the lowest possible for comparison based sorting algorithm, isn't it? And okay, and then the next part for our binary search tree based sorting algorithm, is that also a comparison based sorting algorithm? The answer is yes. Why? Because when we are building this binary search tree one by one, how do we find the right location to do the insertion? We are doing comparisons, right? If we have a new value to be inserted to the binary search tree, we grab this value and then we compare with the root, and then depending on the results of the comparisons, we send this value to either the right subtree or the left subtree, and then we continue doing the comparisons until we are able to find a right spot for this value. So what did we do? We do comparisons before we find the right location. So that's comparison. And then for the in-order tree walk, that is a theta n anyhow, right? So this, well, putting this together, and then this is, well, we are doing nothing more than comparisons, or using make use of a data structure and then to put together all the values into a tree structure using comparisons. Okay, so since it's still a comparison, and then the lower bound, the best case, it is still a omega n log n sorting algorithm. And how about the worst case though? For the worst case, what will that be? Okay, and then how about in this way, let's count how many comparisons do we need to do to build this tree structure in the worst case. Okay, so for the worst case, we let me go back to my drawing board, and then we are trying to use the the bad binary search tree on the right side, and then we have 1, 2, 4, 5, and 6, 6, 8, 10. Okay, so when we insert 1, how many comparisons do we have to do? 0, because that's the first value. And then when we insert 2, how many comparisons do we have to do? We have to do 1. And how about 4? When we insert 4, how many insertions do we have to do? We have 2, right? So the number of the comparisons in this super unbalanced tree structure will be 0 plus 1 plus 2, and then and then plus n minus 1. Okay, so in adding them together, and then you will have an n square there. Why? Because this is the Gaussian theory. Well, and remember, this is the worst case. So in the worst case, and building this super unbalanced tree structure, it is already an n square effort. Okay, and then if we go back and do the in-order tree walk, and you will find this is theta n, but the difference will be here. So what is the effort, or what is the cost to build the tree? And if we are lucky and the tree is balanced or kind of balanced, and then we are expecting an n log n. And if the tree is super unbalanced, and then we will have n square. Okay, so this is discussion of the worst case. And for the average case, then our feeling is, well, it could be n log n if we are lucky, and if we are not so lucky, if we are just in an average case, what will that be? Okay, and then to answer this question, what does the tree building process of the binary search tree remind you? Okay, and this is my argument. My argument is, well, to build a binary search tree, we are doing the comparisons very similar to the partitions when we are doing the quicksort. And let's say, well, if we start from here, this is just a list of the unsorted values. And then, how do we build the tree structure? We are going to grab the first value, and then this value will be the root. Okay? And then, for the values smaller than the root, we are sending them to the left side. For the values greater than the root, we are sending them to the right side. Okay? So if you consider this 3 as a root, and then we have the left subtree and the right subtree. And if you consider this 3 as a pivot, what do you have? You have all the values smaller than the pivot go to the left bin. All the values greater than the pivot go to the right bin, right? So, well, this is really similar. We just grab the 3, and then we use the 3 as a pivot, or the root of the binary search tree, and then we are putting all the values either on the left side or the right left side or the right side. And then for this one, and since this one is the first value on the left subtree, and then this one will be the root of the left subtree. And similarly for this 8 is sent to be the first sent to into the right side, either the right bin or the right subtree. So 8 will be the root of the right subtree. And then if later we have either values either sent to the left side or the right side, and all those values will be compared with the 1 and the 8. Okay, and then if you want to move on, and then for the for the 2, and then this 2 will be compared with the 3, so it's will put onto the left side, and then this 2 will compare with the 1 again, and then this 2 will be put onto the right side of the 1. And then if we just want to continue, the next value is 6, so 6 will be put onto the right side of the of 8, and then this 8 and then 6 will compare with 8, and then 6 will be on the left side of 8. And the next value we have 7, and then for this 7 it will be on the right side of 6, and then for the 5 it will be on the left side of 6. Well, and for this if you want to consider this process as a tree structure building, that is fine. But you will notice that, well, this is really similar to the partition process of the quicksort anyhow. We grab a pivot or a root of a tree or a subtree, and then for the rest of the values, they either go to the left side or they go to the right side. Okay, so well, it seems that, well, you will see the cost of the binary search tree based sorting is very similar to the quicksort. Well, and for the quicksort, on the average case, we have n log n. And for the worst case, we have n square. That is exactly the same to binary search tree sorting. Okay? And then the next question is, Well, it seems that we have kind of a similar sorting algorithm for between binary search tree based sorting and quicksort. And my next question is, which one is better, quicksort or binary search tree sort, and why? So think about this. Which one do you prefer? It seems that the binary search tree sorting is really easy, right? So is binary search tree sorting really better? The answer is no. Quick sort is still the winner. Why? Number one, well, even though they are both n log n algorithms, and remember there is a hidden constant, which is the base number of the log, and then well, a log 10 n versus a log 2n, they're still different, right? And as we discussed before, and quicksort is the algorithm has the best the constant number, so quicksort is still better. But other than that, quicksort is a sorting in place algorithm. And how about BST sorting? For the BST sorting, we do have to build a new array before we can return the sorted version, right? So this is not so cool. And what else? Well, for the binary search tree sorting, we have to make use of a data structure to finish the sorting. And when we are building the data structure in the main memory, and we are consuming more of the memory space. So again, this is something not so cool. So even though for the binary search tree sorting versus the quick sorting, they are comparable. They use a similar idea, and they also do the similar comparisons, but quicksort is still the winner. Okay, and then well, just now we say we can use the BST to do a sorting, and then we say BST sorting is not so cool. So you may ask, why are we learning BST? Okay, here is another application that we can use to make use of the BST. And for example, we talk about the priority queue, right? And then we are having a collection of the items with priorities, and every time we want to grab the one with the highest priority, and well, we discussed that how do we use a heap to facilitate the priority queue, and I use an example of shared printer. Okay, and then for the priority queue, there are a few of the behaviors we want to have. We want to do insertion. We want to find the minimum, and then we want to extract the minimum. And for the insert, we just add a value to the priority queue structure. And then for the minimum, we want to check what is the minimum in the structure, but we are not taking anything out. And for the extract min, we are taking out the node with the minimum of the priority. Okay, and then if we want to use the binary search tree to facilitate a priority queue, can we do that? Okay, and then we can use the same example again. And on the left side, if we say for all those numbers 5, 2, 8, 1, 4, 6, 10, they are the priorities. Okay, and then we are using the priorities of the printing task to do a binary search tree structure, and then we will have a tree structure on the left side, and this can be a priority queue implemented using a binary search tree. And then how do you do an insertion? If you have another printing task which has the priority of 7, for example, and how do we do the insertion? We already talked about that, right? So 7 is greater than 5, we go right, and then 7 is smaller than 8, 7 is greater than 6, so here 7 is going to be here. So this is how we do the insertion. And the next question is harder. How do we find the minimum? Okay, let's come back. How do we find the minimum? So if you start from the root, you want to go to the small side. And the small side should be on the left subtree, right? So you go to the left side, and then for the 2, you still want to go to the left side. You want to visit the smaller left subtree if there's any, and then you go to the 1, and then you still want to go to the left side to find even smaller value, but there's no left child on 1, so when you go left, go left, go left, and there's no more left to go, and then ta-da, you find the smallest value. Okay, so finding the smallest value is not so hard. And then the next question will be, how do we do the extract? When we are doing the extract, this means we want to take out this one. Why? Because this means our shared printer is available, and then we are going to take out a task from the priority queue, and then I want to send that printing task to the printer. So if one is the smallest priority, and we want to send that one to the printer, and then this one will be erased from the tree structure. And that will be the next topic. How do we remove a node from a binary search tree? Okay, so well, I will stop this video here, and the next part we will continue. Okay, bye bye.